Hello, my name is David Lee Jr., and this is my lab focused on studying the motion of a falling object. We're going to start with an introduction of the experiment. We're going to look at the analysis of the falling sock, construction of computational model of sock's motion with gravity, and then also a model with gravity and drag. Then look at the observed motion versus the predicted motion, and then answer some essential questions. So here are some key concepts you need to understand before we get into the lab. This lab is focused on the motion of a falling object. The only two forces working on the sock are exclusively gravity and drag. Again, I'm going to continue to use Newton's second law using the position and velocity update formulas, while also including the force due to gravity, F equals mg, where g is always a constant, 9.81 meters per second squared, pointing down, and drag force is negative b times an instantaneous velocity squared. I have to make an important assumption here that drag has a direction that is always opposite to the direction of the object's motion, and a magnitude proportional to the square of the object's speed. So this means drag will be a force that is going upwards as the sock is falling downwards. And here's a diagram just depicting what I just explained. So this is the sock's motion that I tracked using Tracker. As seen in the video, I chose to drop the sock from my eye level. So I selected the origin to be at the middle of the sock when it was at rest. Because my ball moves alongside the y-axis downwards, the resulting position versus time graph is negative and increasing to the right. The first model I created was a computational model that only considers gravity. I had to apply Newton's second law and iterative prediction to plot the predicted motion of the sock. To construct the model, I used the starter code and updated the velocity update and position update functions to incorporate Newton's second law as shown by the equations. I also changed the mass so the program correctly reflected the correct mass of a sock. I also needed to change the initial position and velocity of the sock. To obtain the correct value for position, I simply placed the coordinate axis on the first analyzed frame at 0 for x and y. So our initial position is a nice 0 vector. The value of the gravity constant is always constant, and j hat was set equal to the unit vector of the y-axis. The proportional constant is 0 for this model as we are not considering drag. To calculate the weight force, I multiply the mass of the ball by the gravity constant and the j hat vector. I again use the starter code to build the model after setting the initial conditions. The while loop is set to end by the same amount of time elapsed in my experiment. Drag is proportional to the squared velocity, so I use the glow script magnitude function to find the magnitude of velocity of the sock, multiply them together, and then multiply the product by j hat to make the result a vector. The net force is then the sum of the drag and weight force. To find b, I needed to plug in arbitrary b values until the last position predicted by the model was very close to the last position I observed in my experiment. In my case, the closest I could get the final position was 0.2 away from the observed final position. And this is a graph depicting the experimental position gravity only and gravity plus drag. In my experiment, the gravity only is obstructed by the gravity and drag as they were very similar. My experimental results differed slightly from the predicted results, especially as time progressed. One of the reasons for this may be the shape of the sock, making it harder for the drag force to impact its motion. Because the sock isn't a uniform shape, as it twists throughout the air, the drag force may vary as it falls. Of course, I could have also made errors when tracking the motion when I was using Tracker, or overestimated the mass of the sock, as I do not have an accurate way to truly measure the mass, and instead, I just used the general mass of a sock that I looked up on Google. I'm going to answer some essential questions about the experiment. What if, and what does it mean? Which models predict a terminal velocity? A terminal velocity is reached when the drag and gravity force are equal and opposite in direction, meaning only the second model, which incorporates drag force, could have predicted a terminal velocity. If the object was thrown rather than dropped, would the terminal velocity be impacted? The terminal velocity would be the same because in most cases, the terminal velocity is specific to the object. The initial velocity has no impact on the object's terminal velocity. This means that the object would still reach that same terminal velocity even though it has a much faster initial velocity. It's likely that the object would just reach the terminal velocity at a faster rate than the object that was dropped from rest. Thank you for watching.